Just like the sign of the first derivative could tell us information about our function and the graph of our function, the sign of the second derivative can also tell us some information. In particular, it can tell us about the concavity of our function, whether our function is concave upward or whether our function is concave downward. If we have a function which is concave upward, the classic example of that is the graph of, say, y equals x squared. That graph is concave up everywhere. You can sort of think about that. I've heard Professor Keep say concave up like a cup, and I kind of like that if you want something to help you remember it. But we also don't need to have that whole shape. We don't necessarily need to include, say, a minimum here. We could only have, say, a part of our graph. So that would sort of be the left-hand side of our concave upward shape. Or we could just have, say, the right-hand side of our concave upward shape. So we don't necessarily need a minimum or a maximum. If you have a graph which is concave down, you can sort of just take all those graphs that I just drew and flip them upside down. So instead of the graph of x squared, we might have, say, the graph of negative x squared. And you can sort of think about this curve as opening downward. Professor Keep has also said concave down like a frown, which I kind of like again. So, but again, if you take these and flip them upside down, this would sort of give us the right-hand side, in this case, of our concave downward shape, and then this would give us the left-hand side of our concave downward shape. So it could look like any one of these. We might have a minimum or a maximum, or we might not. And in order to see why the sign of f double prime of x tells us this, I think if we take, say, for example, the graph of y equals x squared. This is a really nice example here, and I'm actually going to draw it a little bit bigger. So remember that when we look at f prime, when we take our derivative, f prime tells us the rate of change of our function. And if I were to take the derivative a second time, I would end up with f double prime of x. Well, that would tell me the rate of change of the first derivative. It would tell me the rate of change of f prime. So if I say this is a graph of, say, f of x, I'm going to say this is the graph of the original function f of x. And I think about how I can interpret f prime. Remember, f prime can tell us the slope of the tangent line. So I'm going to pick 3 points on my graph. I'm going to pick, let's say, this point right here, and then we'll say this point, and then we'll say this point. So if I wanted to look at the derivative, first of all, at this left-hand point right there, well, the derivative at that point would be the same as the slope of the tangent line to our function at that point. So if I think about what the slope of that is, I don't know exactly because I don't have any numbers to work with here, but I can look at that and say, hey, that slope is decreasing, it's going down. So that means that the slope is negative at that particular point. Now, I chose this point right in the middle right here for a very particular reason, and that's because we have a minimum there, and we have in particular a horizontal tangent line. And if I think about the slope of the tangent line, or the sign of the derivative at that particular point, if we have a horizontal tangent line, I know the slope of our tangent line should be 0 there. So it's changed from negative to positive. And then if I move over here to my final point over here on the right-hand side, if I was wondering what's the value of the derivative at this point right here, well, that's the same as the slope of the tangent line. If I were to draw in my tangent line right there, this is what it would look like. And if I were to wonder what the slope of that line is, I could find it if I knew the equation, but I can look at that and say, well, that line is increasing, which means that the slope must be positive. So here we have something, just to kind of reiterate here, f of x, I've drawn something which is concave up, and it's always concave up. And what I see is that the rate of change, I want to think about the rate of change of f prime. What's happening to it? Well, it started off negative, then it became 0, then it changed to positive. So in this case, the rate of change is actually increasing. the slope of the tangent line is increasing, which means that f double prime must be positive on this particular interval of this particular graph. And you can find a very similar example if you were to look at a concave downward graph. If I look at that just very quickly, if I were to take a graph which is concave downward and think about, okay, this is the graph of f of x, and this is concave down. What I should see is I should see the slopes of the tangent lines at different x values for this graph. I should see those slopes decreasing here. And if I were to take right here, this point, there at that point, my line is rising, so that means my slope is positive. At this point right here, we have a horizontal tangent line, which means my slope is 0. And at this point over here, we have a line which is falling. It's decreasing, so that means the slope of that tangent line is negative. So if I look at how these different slopes are changing, in this case all these different slopes are changing, so the rate of change itself is decreasing, which means that f double prime for this graph must be negative. So this is just kind of a quick little summary of why the second derivative, the sign of the second derivative, tells us whether our graph is concave upward or concave downward. It's a fairly intuitive process, and we can actually use, the good news for this section is that we can actually recycle a lot of the processes that we talked about in the last section. We can use those in this new section, but we're going to be using the second derivative instead of the first derivative.